Hello, welcome to my Dreams Presentation 2025 Spring. My name is Adrian Lee. I'm currently a junior graduating at Johns Hopkins University, majoring in Neuroscience and Cognitive Sciences. It's my pleasure to be here today to share the findings from a fascinating project I was part of, under the guidance of Dr. Susan Courtney and Dr. Howard Egas, and in collaboration with Natalia Kudayari, who recently earned her PhD. Congratulations! The title of my presentation today is Competition between Top-Down Attentional Modulation and Statistical Learning Supports Separable Enhancement and Suppression. In this talk, I'll be exploring how our brain manages the constant influx of sensory information, balancing what to focus on and what to ignore. As we navigate through our daily lives, each of us pays attention to different elements around us, but it's impossible to focus on everything simultaneously. This is the essence of attentional selectivity, that our brain ability to choose what to focus on based on what it seems most relevant at the moment. For instance, as you listen to this presentation, thank you for your attention. You are exercising your ability to modulate this focus. Similarly, when you are driving, it's crucial to enhance your attention towards critical stimuli, like the car directly in front of you, to avoid an accident. However, not all stimuli are helpful. Considering a large flashy billboard while driving, it's colorful and eye-tracking, designed to draw your gaze. Yet, in that moment, your priority is safety, which means you must work to ignore this potential distraction. This process of focusing on the relevant and disregarding the irrelevant is fundamental to our discussion today. In cognitive terms, we refer to these processes as enhancement and suppression. Enhancement involves increasing your attentional focus on targets that are important for our current task. Suppression, on the other hand, involves actively ignoring or reducing attention to stimuli that frequently distract us or are overly salient but irrelevant to our task at hand. Moving on to the main part of our study, we focus on exploring separable mechanisms responsible for enhancement and suppression in attentional process. This study is mainly designed by Natalia Kodayari. My job was about participant recruitment, data collection, and data analysis. Before we delve deeper into our findings, it's crucial to understand that attentional modulation can be categorized broadly into two types, spatial and feature-based. While feature-based attention refers to focusing on specific attributes or object such as color or shape, spatial attention involves the location-oriented selection of cues in our environment. In our study, we especially concentrate on spatial attention modulation. This decision was strategic, as spatial attention could be better implemented in the experimental paradigm. Enhancement and suppression might initially seem like two sides of the same coin, closely linked aspects of how we manage our attention. However, our study sought to challenge this naive impression and explore whether these processes are as interconnected as they seem. If selective attention primarily utilized shared mechanisms for both enhancement and suppression, we would expect to see a correlation in individual differences. Those who are better at enhancing attention towards targets should also be more effective at suppressing distractions. This would suggest a unified mechanism governing both aspects of attentional control. Conversely, there is no significant covariance between these shapes. To your right, that is, if one's ability to enhance does not predict their ability to suppress, it will point towards the existence of a partially separable, at least, independent mechanisms for enhancement and suppression. To test these hypotheses, our approach is to involve correlation between individual differences in enhancement with those in suppression among participants. These methods provide a clear measure of whether processes are linked. However, before doing the correlation analysis, the issue of attaining reliable individual difference has been described in H et al. 2018 and termed the reliability paradox, where tasks that maximize group differences, as many of our popular psychology tasks do, minimize the reliability of individual differences. This poses a serious problem for research involving prediction based on individual differences measures. So let me demonstrate. The data point represents the average behavior across trials for one participant for both tasks. Individuals do not behave like their average value on every trial though. Will all vary across trials, and as we can see here, the gray circle represents the degree of variability of this particular participant. The greater the variability is, the less reliable the average is to predict behavior. To ensure that accuracy of our findings on the relationship between enhancement and suppression, it's crucial to confirm the internal reliability of our measures. Without this reliability, our result can become inconsistent, leading to misleading conclusions. For example, even with the same level of trial variability, poor internal consistency can falsely suggest no relationship between processes, like on the right, while high consistency supports true correlations. Thus, establishing strong internal reliability is a prerequisite before we analyze the covariance in our study. So, as shown here, in extreme cases, the two likely same results will yield completely opposite conclusions. I will now briefly introduce the methodology of our study. In our study, participants engaged in a task designed to investigate the effects of enhancement and suppression in visual search. The procedure started with participants fixating on a central cross on the screen. We signaled the beginning of each trial by dimming the fixation cross for 200 milliseconds. Following a 1-second delay, we presented a search array for 225 milliseconds. This array consisted of various colored shapes, each containing dots. Participants' task was to identify and count the dots within the uniquely shaped item. Our primary variable of interest was the reaction time of the participant. The experiment was structured into separable blocks focusing on enhancement and suppression respectively, with each block containing 100 trials and repetitive. Participants were allowed to rest between blocks to avoid fatigue. In the target learning block, we manipulated the frequency of target location across trials while randomizing the shape of the target. The locations of the distractors remain completely random. Conversely, in a distractor learning block, we manipulated the frequency of the distractor location, while the target location and shape were randomized. This setup allowed us to isolate and analyze how frequent exposure to specific locations influence participants' reaction times, and that's called frequency effect. In target learning block of our experiment, we specially manipulated the frequency of the target's location to appear more often on the left side of the display, while the distractor location were randomized. This manipulation was key to our study of spatial attention. The trial began with the dimming of the fixation point again, following a brief delay consistent with our design. The target predominantly appear on the left, the frequent side. However, in some trial, the target appears on the right, making these trials infrequent. We observed that reaction time was slower in these infrequent trials. This is because participants have had to redirect their attention from the left side, where they had statistically learned to expect their target to the right, even though they are not conscious of this strategy. This shift in attention requires additional time and cognitive effort. This difference in reaction time between the frequent and infrequent trials exemplifies what we refer to as the target frequency effect. In the distractor learning block, similarly, we adjusted the experimental setup by manipulating the frequency of the distractor's location to predominantly appear on the left side, say, while the location of the target was kept completely random. The procedure begins similarly with the dimming of the fixation point, which signals the start of the trial. After the delay, the array appears, and according to our manipulation, the distractor typically shows up on the left, the frequent side. Occasionally, the distractor appears on the right, creating what we classify as infrequent trials. In this infrequent trial, reaction times tend to be slower. The slowdown occurs because participants have adapted to expecting the distractor on the left was now recalibrated and suppressed a newly placed distractor on the right. This re-implementation of suppression mechanism depends on additional cognitive effort and time, leading to increased reaction time and a higher likelihood of error. We refer to this variation in reaction time as the distractor frequency effect. So here is our result. I've skipped some previous version of the experiment and only present you with the final version. So in this final version, in our enhancement task, let's turn our attention to the distribution of the 5,000 estimate displayed to your left. On this graph, the x-axis represents the SB corrected correlation coefficient, while the y-axis shows the scale density of these estimates. Notice that the blue bar on the graph which delineate the 95% confidence interval. Importantly, this confidence interval does not cross zero, a key indicator in our analysis. The fact that it does not cross zero indicates that our enhancement task produce reliable individual differences in enhancement strength. This robustness in our data underscores the effectiveness of our task in measuring the targeted cognitive process. In our suppression task, less so, let's pay attention to the 5,000 estimate as well. Similar to the enhancement task, the graph plots the SB corrected correlation coefficient against the density. The fact that 95% confidence interval remain above zero confirms that our suppression task reliably measure individual differences in suppression strength. However, as you can see here, in suppression, such confidence interval is closer to zero, which was the previous difficulties in other experimental descent that didn't successfully address the problem. So now we have confirmed the internal reliability of the two measurements. Now turning to the relationship between enhancement and suppression strength, which are plotted on x and the y-axis respectively here on the left. Our analysis reveals an interesting finding. There's no significant correlation between these two measures. This suggests that the process underlying enhancement and suppression might not be as closely linked as one might assume. Given the importance of making accurate inference from a null result, we extended our analysis to include a Bayes factor analysis, which is on the right. This analysis provides us with anecdotal evidence supporting the null hypothesis, indicating that there is no significant correlation between enhancement and suppression strength for now. This finding points to the possibility that some aspects of suppression are separable from enhancement, while they are not completely independent since they are definitely shared mechanisms, such as traits like conscientiousness affecting both. There's a part of suppression that operates distinctly from enhancement though. This is a crucial insight as it suggests that our understanding of cognitive control is more nuanced than a model of purely shared mechanism would suggest. Our result leads us away from the assumption that only shared mechanisms govern these cognitive processes. So that was the main study. Now let's discuss some intriguing aspects of this study concerning the effect of self-reported engagement from a side study. But this is actually emerged as an unexpected finding. This study is conducted largely by myself as a side project to the main enhancement and suppression study done in the lab. So, in our effort to delve deeper into the factors that might differentially influence suppression and enhancement, we considered the familiarity with the testing environment as a potential variable. To explore this, I designed a follow-up study with two distinct sessions for each participant, a movie session and an attention session. The attention session utilized the exact same experimental setup as our previous study, where participants engage in tasks designed to measure their enhancement and suppression capabilities respectively. This session is crucial for gathering our primary data on cognitive control. In the movie session though, participants were simply asked to watch a movie in the same testing environment where the attention session will later occur. The key was here was not the content of the movie or the participants' reports on it, but rather the opportunity for participants to become familiar themselves with the surroundings of the testing environment, even though they are not conscious of it. This session lasted 1 hour, designed to reduce novelty effect on the environment in subsequent testing. Therefore, participants were scheduled to return 2 days later to ensure that the setting remained consistent but allowed some temporal separation between sessions. We divided participants into 2 groups. The familiar group, who attended the movie session first, that's becoming acclimated to the testing environment before the attentional session, where the data was truly collected, and the novel group, who did not have the familiarization period and experienced the environment for the first time during the attention session. After the attention session, we also conduct surveys to assess other potentially influencing factors, such as sleep quality, stress levels, and overall engagement during tasks. Contrary to our hypothesis, though, the results were in fact largely trivial, showing that there is an advantage for the familiar group over the novel group in terms of their ability to suppress and enhance stimuli. But the advantage is not differentiated between these two, which are the actual interest of our study. So that result was merely trivial. However, our analysis did not end there. The survey data collected post-attention session provide us with some intriguing insights. In presenting the results from the familiar group, we have divided our analysis into 2 key components, target learning and distracted learning. On the left side, focusing on the target learning, our data reveals a noteworthy difference between participants based on their level of engagement. Interestingly, highly engaged participants did not exhibit as much target learning as those who were less engaged. This suggests that lower engagement might paradoxically be associated with more effective statistically learned enhancement in this context. On the right side, when we look at distracted learning, the finding invert. Here, highly engaged participants demonstrated significantly greater ability to learn suppression, or statistical suppression, as evidenced by their higher level of distracted learning compared to their less engaged counterparts. This indicates the higher engagement facilitated better suppression of distractions. Recent research in cognitive neuroscience has started to unveil a fascinating dynamic in our understanding of attentional processes. There's emerging literature that points to a competitive nature between statistical learning and top-down modulation of attention. This body of research suggests that these 2 systems, though both crucial for efficient perception and behavior, may actually compete for cognitive resources. So, upon revisiting the familiar group data, particularly the highly engaged individuals, we gain deeper insights into the dynamic of top-down control of attention. High engagement, which reflects strong top-down control, reveals interesting patterns in performance that could further support the hypothesis of competitive mechanisms and the separable hypothesis. Firstly, we observe that strong top-down control in the form of high engagement significantly impact targeted statistical learning, that is, the leftmost column. It appears that when individuals exert a high degree of top-down enhancement, it can actively diminish their ability to learn from statistical regulation, so they were not aware and they were not reacting as if they were, involving targeted stimuli. This suggests a competitive interference where focused attention disrupts the processing and integration of regular patterns in the environment. Conversely, when it comes to distractor statistical learning, the effect of a strong top-down suppression presents a different scenario. Here, a high engagement does not seem to negatively impact the learning of statistical irregularities related to distractors. This divergence implies that the suppression exerted by top-down control might operate through mechanisms that do not interfere with, and even may coexist with the learning of patterns associated with non-target elements. I know that was a lot and there was a bit confusing terms and concepts. So I'll just reinstate my preliminary findings and conclusion from this data. So a strong top-down attentional modulation, that is, engagement, will affect enhancement and suppression differentially. This supports that the previous finding that enhancement and suppression is partially separable mechanism as the same factor exert different effect on two processes. This may also be supplemental to the competitive hypothesis that statistical learning is in competition with top-down modulation, because maybe competition is only in enhancement, not in suppression. Now we need to discuss some downsides of the study. One particular question remains is such trend does not exist in the data analysis of the novel group. The novel group shows no distracted learning when engagement is high, but do show target learning when engagement is high. So the fact is kind of reversed, but there's no working hypothesis on this. So as discussed, there's still a lot need to be done. And the study, the number of subjects for a study is in the range of like 50 to 100, which is not a lot, but significant enough for a behavioral study. But it might come with suspicions. So these are the future directions of our study. We should first investigate the reason why the same trend does not appear in the novel group, or even the opposite. In order to do that, we probably should expand our recruitment of the participant just to make sure if we can replicate the same effect. Second, we should consider whether the self-reported engagement level is a reliable measure, as this has always been the suspicion correlated with a behavioral study, as maybe this factor is confounding with other factors, such as a reported task difficulty. So maybe it is how the participant consider the task to be difficult or not that is truly impacting their enhancement and suppression behavior. Or there could be potential biases introduced by the task introduction, as the task is always about finding the target, and there's no per se attentional or emphasis on distractor. And third, we should probably consider incorporating some other neurophysiological data if we can have the participant completing the study on the recording of ERP EEG machines, so we can have ERP or oscillations analysis. And finally, we should also consider whether such effect is limited to spatial statistical learning, as that's the only thing we have been studied. As we said, there are mainly two categories of statistical learning, and we should probably think of feature-based learning and feature-based attention. So now, just to express my thanks to my lead graduate student, Natalia Cagliari, as the main study was her idea, and my side project was in support of hers, and I appreciate it, as if there's no her original idea, there won't be this study. Also appreciate Joshua Sewell, Nathaniel Glenn, Alan, who are my lab mates in the Courtney lab. I also like to thank Dr. Hoa Egith, who introduced me into this lab and these wonderful projects. And also my special dedication to Dr. Susan Courtney, as she has passed away a year ago. And this will probably be the last project of the Courtney lab. And here are my references. Thanks for watching. Bye.